let's say we do not have C3 rotation axes. In that case, we need to ask whether we have n C2 axes which are perpendicular to our principal axis Cn. If this is the case, we need to look for horizontal mirror planes. If we do have those mirror planes, we will call this point group DNH. And here you see how such a molecule would look like. It's a simple square, but remember we have to orient the square in a way so that the axis with the highest n, our principal axis, is pointing in vertical direction, and in this case this one is our principal axis, and this is a C4 axis, meaning that you could rotate the square by 90 degrees and you would bring the compound to superposition on itself. Let's see if we find also the n, meaning in this case 4 C2 axes. They're right here. This is number 1. This is axis number 2. Axis number 3. And this one here is axis number 4. And in addition, you have a horizontal mirror plane which you could define, and this horizontal mirror plane is the square itself. So you end up with a point group DNH, and in this particular case it's D4H. And this could be our example, xenon tetrafluoride, where you have the xenon in the center and the fluorides at the corners of this square. If you don't have a horizontal reflection plane, we need to look for a vertical reflection plane, sigma v. If there is such a reflection plane, we call the point group DND. Now this D here stands for a reflection plane which is everything but in horizontal direction. And here is our example structure which represents such a point group. And as an example, we want to discuss CH3, CH3. The carbon atoms are located here, and there's a single bond between these two carbon atoms, and here at the corners of this tetrahedron on the top and here at the bottom there are 3 hydrogen atoms. Now there's a C2 rotation axis right here at the center of the molecule, and what happens if you apply this C2 rotation symmetry operation is that this hydrogen atom up here after the rotation becomes this hydrogen atom down here. This one becomes this one, and this one becomes this one. So this is just one out of 3 C2 rotation axes. The other ones are here and here. In addition, we also have a vertical mirror plane. Now this vertical mirror plane can go through this hydrogen atom here, the 2 carbon atoms and this hydrogen atom down here, and also through this hydrogen atom, carbon atom, hydrogen atom here and here. So meaning we have also 3 sigma V reflection planes. And not to forget our principal axis, which goes through the entire molecule, this direction, and to the center of this triangle up here. And this one here is then our C3 principal axis. If we do not have a vertical reflection plane, then we call this point group dN. I want to use the top-down projection this time. So what do we see when we look from the top to the bottom of this molecule? Up here we see 3 hydrogen atoms and the carbon atom in the center. So here's the carbon atom, and then here there are the 3 hydrogen atoms. Then we have the next carbon atom, and what I'm using here is actually the so-called Newman projection, and in order to point out that we look in this direction from top to bottom, we draw this ring structure here, which represents basically these carbon atoms here, and then we have the hydrogen atoms in the lower part of the molecule, which are those here. And now we can define an angle, the so-called dihedral angle, between the hydrogen atoms of the lower part of the molecule and the upper part of the molecule. So let's call this angle here phi, and phi is, as I said, the dihedral angle, so the angle between this hydrogen atom, then these 2 carbon atoms, and then the next hydrogen atom in the bottom structure. Now, if this phi is equal to 0 degree, then we call this one an eclipse structure, meaning that the hydrogen atoms in the top tetrahedron and the hydrogen atoms in the bottom tetrahedron are covering each other, and in that case we would call this point group D3H. So remember, just in this case where we have a C3 rotation axis, this N would become a 3. Now if this angle phi is equal to 60 degree, which is the so-called staggered conformation, then we would call this point group D3D. And if this angle phi is between 0 degree and 60 degree, then we end up with the point group D3. Here you can easily see where the principal axis is located. So this one here is the C3 principal rotation axis. And here is the C2 rotation axis, which goes through the center of the molecule. And there are 3 of these C2 rotation axes.